Good evening. So, secure boot and TPM-backed full disk encryption. Don't let the title scare you. This actually contains multiple subjects. You might be familiar with that. Not only that, you may actually even apply it on your Linux installation, on your environment, secure your setup. What I try to do is actually what I attempted, put multiple things together, and top of that, I try to enable secure boot and integrate the whole system with the TPM, which is the module I will also briefly touch. Prior to start the talk, actually, I would like to refresh our memories, how the Linux boots up, which could be quite relevant. Well, we can start the powering on the device, and there will be an initial check takes place. The hardware components will be initialized. I think you can include maybe keyboard, mouse, but also you can exclude them, because you may even access this device via KVM. So even maybe monitor is not connected, and our focus is basically be sure that hardwares, most importantly hard drives, storage units actually are initialized, and specifically one where the operation system installed, so we can actually boot the system up. But at first the bootloader must be loaded, and here I didn't choose arbitrarily group bootloader. It is significant, and UEFI is also significant. I will also touch them later on. After the bootloader is loaded, kernel will be loaded, drivers are loaded, and system services will start, and then the user space will be available for the user. However, if you just pay attention to the highlighted bold text over here, verify signature using secure boot. So during the early boot, there could be one more check, one more verification actually may take place. What is it could be the secure boot actually if we enable it. And what it does, well, it basically ensures that the group bootloader, the bootloader in general, is verified, and also prevents unauthorized modifications. So what does this mean? Well, let me actually tell you how the secure boot first works. Well, there are two ways it can actually kind of operate. One way, well, we can consider is the out-of-the-box way. Regardless whether it is enabled or not, there are, if you check the UEFI, you can find where the keys are located there and stored. You will see that there are already signed keys and generated keys and signed, and these are the keys will be actually handled basically the secure boot. In other words, trust chain will not be owned by you. Trust chain will be already done by the secure boot. Actually, the Microsoft will handle this process, especially by signing the shim, which will be significant in a moment. The other approach will be that, well, basically, you are not using these generated keys, and you are generating your own keys. If you look a little bit more deeply, so I already mentioned the shim and the Microsoft. So actually, Microsoft behind the shim and signs the basically shim, and but what are those keys? Well, we have actually kind of four categories. One is the like public keys, key exchange keys, and the authorized keys. There is also one more. I will get into it later. So DB is basically stands for the authorized keys. So what happens? Well, we are actually creating a trust chain. Actually, trust chain is already exist, signed, and we are just basically using it, relying on it. But there is one thing that we can do. We can actually use mock-util. After the operation system up and running, we can actually a little bit modify this trust chain, but we have a limitation. We don't do any other things. We are just relying on the existing keys generated by Microsoft and already signed EFI binaries, and as well as the kernel. In fact, if you check the kernel and the EFI binaries, you will see one or two certificates there. One could be from the Microsoft, and one could be from the operation system, for example, from the Debian. On the other hand, if you want to go to like a full ownership, then what we can do, we can actually replace all those keys by the ones we are generated. So in this case, we are actually basically deleting all the keys, public key exchange key, authorized keys, and maybe, as I said, there is one more category, and then sign EFI binaries as well as the kernel with the ones we are generated. So here we are actually owning the whole trust chain. And you can actually see the comparison to each. So as I mentioned, the shim is actually kind of important here when it comes to the default approach, where the shim is signed by the Microsoft. And if you go to customize approach, where we are owning all the keys, and we are basically excluding the shim, and then it starts still the same. We still have the same number of keys or the same type of the keys, but the verification process is actually now owned by us. Basically, we are owning the trust chain. So my presentation will be quite fun because I'm going to quite hands-on, and I also learn this subject as I go. So I will show you the bunch of commands here, and I will try to also explain why I am using them, on what purpose. And here, actually, if you want to, for example, enable the secure boot, and you need to install some packages. Because I do experiment with this, there are more packages here than required. For instance, UEID runtime may not be needed. You may come up with your own way to generate your UEIDs, or you may have already some implementation mechanism. But the mock-util is necessity, because we have to use the mock-util to verify the secure boot status, which should be disabled, and also it should be in the setup mode, which I will also tell you how we can do it. And after that, well, in order to organize things, because we're going to create many files, and in order to keep things organized, I recommend you to create some folders. This is not, again, like a necessity. You can do this in a different way. You can place them in another way, in other places on the machine, but just don't forget where they are. So as I have mentioned, you need to disable the secure boot. So this is maybe not the same on every machine, on every device, but you need to find the secure boot, and then you need to disable it, and then you need to actually go basically delete all those keys. And here you can see also forbidden signatures, which is called DBX. And this is kind of preventing for malicious software to be executed on your system. Not only after the operation system is booted up, but prior to that, during the early boot too. Because there could be maybe a malicious software during the early boot and try to connect the internet or something. And I will talk about relevant things later on. So it is up to you. You can actually delete it, or you can come up with your own forbidden signature as well. So now this is where the fun begins. So first of all, you need to create platform key. Oh, I actually public key, right? Yeah, okay. It's a platform key. You need to create platform key, key exchange key, and the authorized keys, along with their certificates. Here, the subject, you can see I just put there an example, but you can actually enhance this. You can actually a configuration file, and you can actually target the configuration file, and then you will have more detailed certificates, like the email address, expiration date, multiple CN. This is just the simplest way, so I can actually talk about this. But you can actually improve this basically. And after that, and again, generating the random keys, I am using a command. Again, you can actually generate it in another way, but it will be better to actually create one UID and then keep it, and then you will use the same one later on. So the second step after generating these keys, basically generating, also converting the certificates to UEFI signature list. And after that, you need to also create sign authentication codes. And after that, again, you can actually work with the unauthorized ones. It's kind of up to you. I haven't actually practiced that. I basically deleted it during my experiment. But the most important thing, silent the kernel. So here you can go strategic, because when you have the operation system, you may have one kernel there already, of course. But then later on, let's say you have Debian and you're gonna update the system, and you can see there will be another kernel, for instance. So you need to sign them. Well, you can actually sign them both. How many kernels you have, you can sign them all of them, or you can just make sure that only recent one is the signed. So the previous ones, if somehow machine some reason try to boot up from the old kernel, then it will not work. So you will have all the control of how the operation system boot up, and what kernel, which one, and should be basically allowed. Again, it's a strategic decision. You can sign them all too. So now, after that, basically you need to actually sign you sign the EFI binaries. So here I am also signing the shim. You may exclude it, During my experiment, I actually wanted to be sure that everything works. So I signed basically all the UEFI binaries. But some cases, I have observed that if you delete the shim, you may get some error messages during the early boot. So you may need to little bit experiment with that. But one thing is important. These UEFI binaries are not, let's say, empty because they are already signed. Again, they might be signed by the Microsoft as well, and also there could be a signature on them comes with the direct operation system. So at least there will be one. So you can actually check it. What I'm trying to do by running these commands, basically I am trying to actually create empty ones. And the reason I try to do empty ones, because you cannot directly actually add another signature on them. You cannot sign them. You need to basically get rid of the existing one, create an empty one, and then you will be allowed to sign them. After that, in the last commands, I am trying to actually get rid of all the empty ones. So now we have already signed them, but this is not going to make any impact on the system because we basically enroll these or custom generated keys to trust chain, into the trust chain. So there are two ways at least we can actually enroll them. One way will be basically running the UEFI update var, and this is where this path comes in handy because you need to basically access the out folder in that path and then target those files. Or you can use the secondary command, but if you use the SB key sync, then be aware because you need to run it 2 times. At first try, it will only enroll the platform, it will not enroll the platform key. You need to run it second time, and if you try to run to enroll the platform key, you may get some error messages. If you don't get an error message, it may look like it worked. I tried a couple of times. I am not 100% sure whether because I try to enroll the platforming key first, but basically it will behave unexpectedly. So it will be better to actually follow these steps and then enroll all other keys and the platform key first. So far we are talking about the secure boot and the owning the trust chain with our own generated keys. However, this is just will apply during the boot process. What if our data integrity? Machine will boot up and we have the system up and running, we have our data. When it comes to protecting that, we can also talk about this encryption, and fortunately Linux already support LUKS2 out of the box. So it's quite detailed. There is so much actually configuration you can do. I'm not going to get into detail, but I will just bring your attention. LUKS2 and LUKS1 will be relevant to us, and for now I am just focusing on the LUKS2, but later on I will also mention the LUKS1. So here basically what I'm going to do, yes, you may even see the password here, 1235 is just I put it there because I wanted to show you how the command works. You can also come up with your own automated way to generate very secure password. But basically what I'm trying to do, try to format a partition on the hard drive and encrypt it with the LUKS2. And then set a password. And then I open that encrypted hard drive so I can format it. After I format it, what I need to do, I need to actually have add this decrypt tab. So if you have a hard drive, a partition, it will have a UID. But if you encrypt it, and then its UID will be different. So in order to actually operation system to know that there is an encrypted partition on your system, you need to have that edit the crypto tab. If you don't do that, if it is not a boot partition, machine will boot up, but then you need to go manually actually open that encrypted partition later on. So putting here the crypto tab will basically, it is sort of necessity, and you will not like block yourself out from the system later on. But again, machine, the system will boot up because boot partition is not encrypted. But it will be better to put here. And then you need to definitely update the init RAMs. And if you don't do that, you may get some error messages, system may not boot up. Also, this configuration could be different based on your needs, because so I would suggest you just check how you can run init RAMs in a different ways. Most importantly, even though here these steps you can follow to encrypt a partition, I actually don't recommend this, because if you have an operation system already installed, it is really dangerous for you to encrypt the system while there is an operation system there. So it can cause a problem. It can cause like a data corruption, and even though you do everything right, operation system may not boot up. So what maybe I cannot give you a statistic, but it is not ideal way to do that unless you are really sure that we are backupping everything and restoring it. But it is unnecessary too much work to me. The best practice, I think, you can do this during the installation process. You can just, for example, follow the UI or the command line during the installation process and choose the right option for your needs based on your needs. However, and this could be a little bit tedious process, because if you wanna do it multiple times, I recommend you to create unattended installation. This actually makes life much easier. Debian has a way to do that, which is sort of nightmare. The configuration. I think Arch is way better, but I focus on the Debian. And basically, you need to create a, I guess called preset config file. You need to play with that. You need to come up with your own configuration. And in the end, you will actually have LUKS2 encrypted system installed on your machine. And then what will happen after that? Either way, when you reboot the machine, you will be prompted with this to tells you to unlock the hard drive. So this is after the boot process. Actually, this is after the early boot process. So machine is about to let you to user space. But every time entering this could be, I think, annoying, and you may not even access the system to do that. So you can also automate this process by generating a key, which securely can be kept actually under etc and keys. So there are various ways to you can generate these keys. This is just one way. And the most important things, after you generating this key, you must add the cryptos. You must add it using the crypto setup, and then after that you need to also update the crypto tab again. So previously we didn't updated it. We only actually updated the crypto tab to tell the system, hey, I have an encrypted partition here, and be aware of that, and basically tell me to unlock it. But now we are not actually doing it. We are basically telling it, hey, I have an encrypted partition here. You don't need to tell me now. You don't need to prompt it. This is the key file, and this encryption is actually takes some time. And the way I see it, based on out of the box, when you do that, if there is no any other key edit using the crypto setup, then it will be in the slot 1. So basically you can target the slot 1, and it will speed up the encryption process. And after that, again, you need to update the init ramps. As I have mentioned before, you can check the configuration for the init ramps. You can do it in a different way. So basically you might not necessarily need to use the all if you find the more relevant configuration for your needs. So now this is actually gets much interesting. We were talking about encrypt maybe the rest of the partitions where the operation system, where your the data are stored. What about the boot partition? Can we encrypt that? Yes, but the most important thing here, we cannot encrypt with +2. At least the way I found out, based on my experience, my experiment, it didn't work. Also, I kind of found out that it is not supported. It only supports the LUKS1, not the LUKS2. So maybe there is a update now. It supports now LUKS2, but by the time when I was actually working on it, I had to do LUKS1. So so basically you can, yes, encrypt the boot partition, but you must actually remount in a only readable way, because during this process nothing should be written the boot partition. So basically you can backup in it, and then after you backup it, you are still following the same process. You can see here more commands. These are just actually for you to kind of know. You can actually come up with different, like a configuration. You can enhance this encryption process, again, based on your needs. And here is a significant part, is the LUKS1. So after that, you need to format this encrypted partition, which is actually our boot partition. And after that, you need to restore. And after you restore, you can actually go and check the f-stop. I didn't actually see here, but you might need to also go to look at the cryptotop as well. I think that part is missing here. So basically, you need to be sure that when you are encrypting anything, UIDs are changing. If any place on the operation system that UID used, you might need to go and update it too. So this encryption, and if you do this, this will not work. This will not work because you need to actually enable it. And the only way to enable this, which I learned from the hard way, because I did this and I was very happy about that, then nothing worked. But luckily I got an error message, says that error message, it literally tells this one, group enable crypto disk. It literally tells the same things. You need to enable this. Okay, so it is not actually kind of complex process, fortunately. You just need to update this. In other words, you need to enable this in the configuration, and after that you need to regenerate the configuration. But later on, you need to now install the group again. So here's the tricky part. Here you may see, actually I am pointing at path, boot, EFI and EFI. And I use Debian. The reason I use Debian because I did this on Debian operation system. I also tried on Ubuntu, didn't work. But if you, let's say you're trying on Ubuntu and everything works so far, and when you come here, don't put there a Debian because Debian may not exist. You may have another distro, so you need to go and check what you have under the EFI, and you may have multiple. You may have Debian or maybe something else, and you need to basically tell the group install where you are installing the EFI binaries, because if you don't, it may create its own, and then things may not work, and you may actually kick out yourself from the operation system, and it will not boot up because it will not find the UEFI binaries. Then you will end up in the group rescue mode, and it's not fun. So if you get here, and if everything is done after rebooting the system, now it will tell you enter the passphrase right away after the all initial check is done. So basically, during the early boot, you will actually get this. It kind of it's funny because you can see like some like logo, some maybe messages comes from the factory settings. You can see the hard drive are like initialized, and then suddenly you will see enter the passphrase over there. So it kind of looks UI wise not like visually tells you to enter. So just pay attention. The text could be a little bit broken. And this UID is actually kind of significant because you will see this is one of the configuration file. Now, it is also kind of not, I guess, convenient to enter the password every time when you boot the operation system. You can also automate this process. By the time when I was actually working on this, I used a group 2.13. However, either 2.6 or 7, I might be mistaken, but one of the earliest version also supports this. So what I mean by the support is, this is kind of fun. When you install the Debian, you can still boot, encrypt the boot partition, but you cannot do auto unlock because it just so happened there is one binary called, I guess it was the crypto disk, and it doesn't support auto unlock. So you need to build the group bootloader from the source code and reinstall it. And if you do that, you will have the updated version. When you have the updated version, this binary will come with that feature, so you can actually unlock the boot partition without entering the password. And again, the 2.13 it support this, but one of the previous versions support this as well. And I actually kind of recommend not to use this one because this is kind of heavy. It comes way more features. And basically, if you just only need to unlock the boot partition, like automated way, then look at the most recent, earliest version possible. So basically, you need to download the repo, and based on the documentation, these are the steps you need to follow in order to actually build the bootloader from scratch. And there are some modules. These are the modules are required because when you build the group bootloader, these modules will be basically included. There are more modules you can have, but these are the most important ones. So After you reboot, let me see. Yes, automate unlock. So you reboot, maybe, yeah. So you reboot and it will still prompt you to enter the passphrase. That means anything you have done here worked. Nothing is broken. Machine still can boot up. So this was like some sort of like a security check. But you wanna basically automate this unlock process. So what you can do, you can basically create your own custom group configuration. In order to do that, you need to basically edit or generate this group file. So question mark here is actually the things I am trying, I have been emphasizing since the beginning. These are the UI IDs. Either you can put the UI IDs or the name of the partition. Like if it is encrypted, it could be maybe like a SDNX encrypt. So you are putting there the encrypted UI ID, and then the set prefix will be the one after the encrypted partition unlock. So you can actually go cryptotab and the fstep. In those files you can see fstep is the encrypted one, and the cryptotab is where you can see the UI ID for the encrypted partition, and after it is unlocked it has a different UI ID, and which will be in the fstep. Or you can use the name too. Actually you can use the name in the fstep. After this, now you need to basically embed this generated your custom configuration to the EFI binaries. When this is done, when you reboot, you will see still the same prompt, but after that slot 0 open. So basically you will no longer need to actually enter the passphrase. One disadvantage is this. When you do that, I actually spent like I guess 20 days on this to figure it out. You broke the secure boot. The reason is that you are intervening with actually the of the EFI binary, and even though you are generating EFI binary and signing it later on, secure boot is basically not happy about that. So I have actually tried various different ways to find out. I haven't actually figured it out. Couple things I'm still trying on. As soon as I found out, maybe in another talk I will let you know. So you need to prioritize things. So far everything works, but you need to prioritize. You need to secure boot, or you need to have boot partition encrypted. So we have now encrypted the hard drive, completely. The partition where we have the operation system, where the data, and also the boot partition. But we can also enhance this, enhance the security using the one module called TPM, a trusted platform module. This is basically we are shifting from the pure software security to also hardware security. This is a small module. I guess laptops also has it. You can laptops also have it, and you can see it actually whether it is enabled or not on the UEFI, and you can enable it or disable it. But even though it's enabled, even it is there, in order to actually use it, of course you need to install a couple packages. And well, this is for the only TPM2. There is also TPM1, I suppose, and anything I do here should work with only TPM2. So you can basically install the required packages, and you can check the version, and after that there are various different ways also check the status of the system. And if you just look at here the TPM2, and this is a significant one, because maybe you have the TPM1 and then you will not actually see here because you are already installing packages for the TPM2, so it will not support completely. And I just have this here just for you to know basically, and during my experiment I needed to find out to get familiar with the TPM, how it works, what can I do with it, and I was basically running various different commands to see whether I can see anything relevant to my work. So you have the TPM and you checked it, it is there and it is working. Now what you need to do, you basically own the TPM, because you can actually use the TPM without not any ownership, but that will basically security breach, because as soon as operation system is boot up, anyone who can access the system as a user then use the TPM, and that actually kind of diffuse the whole reason that why you are working with the TPM. So again, of course, you need to have more secure password here. In fact, you don't need to even enter this password. The almost everything you have seen here so far automated using an Ansible. So after the operation system is securely installed, I basically run the Ansible playbook. It actually handled all the whole the process, and also generate all those the password. And I also use the vault, so I don't even like see what passwords are generated or used. So you can own the TPM, and after that you can actually start to play with it. Let's say you have one data sealed. So this is actually important because I say sealed, not encrypted. You may have already an encrypted data, and what you are doing basically, you are sealing this encrypted data or the data you have on TPM and keeping in one registry. So it can be a text, it can be a public key, which we'll actually also talk about a little later on. So we are basically creating a primary key, and then you are using this primary key and load the data to volatile memory. What does this mean? At this moment, after it is loaded, it is there, but if you reboot the system, it will be gone. So in order to persist that data, you can actually use another command and your password, the ownership password. So basically, you can persistent data. And here, I am actually explicitly mentioning what address I want to put in. And then when I see it, it is persisted in that into that address. What if I want to unseal it? So because it is persistent, it's in the non-volatile memory, I can basically get all the persistent like addresses that in use, and then I can actually unseal what is there, and then if I wish, I can also basically remove the persistent handle or the basically what is there. So this is just a quite minimalistic way actually working it. We have also a TPM also support the policies. I guess it's configuration registry. I don't remember what the P stands for. I guess a configure registry. So basically, you can create your custom policies. So this is the part that's a little bit tricky because these numbers are here actually corresponds to policy. Each number actually corresponds one policy. If I collect the 7 correspond to secure boot. So what does this mean? Basically, you can put there 7, and if the secure boot is enabled, and later on, if you disable the secure boot and you have TPM set up using the policy requires 7, then it will not work. So basically, you will not be able to unseal the data because the policy now is not matching with the configuration. The previously the configuration. Because you changed, for example, the setting. And the other numbers here also indicates the other settings, and there is a list for that. I guess there are either total 15 or 20 settings, and this is kind of not only just it is one thing, not only 7 is the secure boot. We talk about the secure boot, but it's a trust chain, and the trust chain is not just necessarily one thing verifies the another thing. You can also consider this like one thing verifies another thing, but then 2 other verification needed to be done. So it's basically you can consider actually the hashes. You have UEFI binaries, you have kernels, or even though they are signed, even though secure boot is enabled, and they are signed with the keys that you have generated. Let's say you updated the operation system. Now kernel maybe got changed, or you copy a file from another operation system, exactly the same UEFI, and sign it. But the hash will be different. Because the file hash will be different, one of these policies actually will be still the problem for you, and it will say it will prevent for you to actually unseal the data. So you need to pay attention what policies are using in what order also. Because some policies will be applied during the early boot, some policies will be take effect after the operation system almost boots up. So let's say the late boot. So here what I'm trying to do basically, I'm trying to start a session. Why this is important? So I am creating a session, and during that session I am also creating the policy, I am generating the password, and then I am basically getting it off this session. So after that I can actually create a new primary key and seal data. So after data is sealed, I can still load this data, but if you want to unseal this data, I need to create a session again. So this put maybe some sort of one more level of security too, because you may not know whether session needs to be created. And in that specific session, only in that specific time window, as long as the session is like let's say started, exit, I will be able to use the policies and unseal the data. And of course that after that I will flash the session. And here's the thing, let's say during that time you started the session and you put there, let's say 7, and you didn't configure the 7 previously, so 7 was not here actually, it was not there, and then you put here 7 during the actually sealing process, and then you will get of course an error message because the policy now is not matching. You cannot continue after this moment because now you you need to create a session again. So this is kind of actually makes things a little bit more challenging. So every step, everything should works. So basically, if it fails, you need to start the session again, and you need to write actually the numbers here. So you can then after that you can unseal the data. But everything here you have done still required maybe manual work. What if we can also automate this process and maybe have it done without like a user interaction? So in Linux we have an option to actually come up with custom initram, basically configure the initram. This is quite simple way to show you. It's a little bit actually require more explanation, but if you go look at this part, it's in initram tools, you will see scripts and the hooks, and the hooks here will takes place before the scripts are executed, and there are scripts basically that are like a 6 level. So 6 level, and it will take in different time at different time during the early boot. So based on your needs you can actually create custom scripts in order to do some operations, because during the early boot, as soon as initram is loaded, you can actually access the internet too. Maybe you need to pull something, for example a fetch a secret from a URL, or make request in an endpoint, get something, it will be possible to do that. So here there is some configuration. I actually kind of play with this, but so far what I found, this is the way to go. So if you change it, it may not work. This basically how it's supposed to be. So this is basically you can consider as a template. What I do though here though, so during the initram, well, you can consider this bare minimum operation system. There are still binaries that can be there, and you can use that binary, so you can execute stuffs, but you need to have those binaries available. So you need to basically binary by binary you need to define them and where they should be. So let's say you need to use load external. This could be any binary, by the way, like for example the mount, so or build ID. So if you need those binaries during the initram process, you basically need to have them available there. And there it is again the syntax of the this script, so you must have that there too. So basically what you are trying to do here, you are ensuring that these folders will exist and during the initram with this actual permission. So why I am doing all those things, so my goal is here actually one more thing, as I mentioned the scripts, so there are multiple scripts and they run in different different time, and the one I used was the local tab, and I just want to be sure here with this implementation local tab runs last. So firstly the hook script must be executed, so I have all those folders binaries ready for me, and then the anything in the local script will start running. And what I do here, I do basically we can also debate about using hard-coded UID, but my point is here, be sure that I can actually have USB drive with this UID and mounted this path. So if I don't here have this mount binary copied, then during the initram process, when I use the mount, it will not work because it doesn't exist there. So that's the purpose. Now I can use it. After that, what I'm trying to do, actually, I try to get a file there, which I didn't mention here, but the purpose is here. Basically, during the early boot, you can have like some sort of maybe a public key, which is actually stored in the USB drive, the specific USB drive, and then you are sure that this file is needed, and then you can integrate with the TPM to, for example, uh, we have policies, we have the key, and you can actually customize this process, and you can make sure that only this public file will be used, and then you can unlock, for example, the encrypted partition. So here the goal is here make everything fully automated. This will take after the early boot, after the boot partition is decrypted. So we are not actually doing anything for the boot partition. If you encrypted boot partition, it will be still encrypted because we already actually embedded our configuration to EFI binary. So that will work, and group bootloader will be loaded. But what we are doing here is for the second part, basically, where we are entering the passphrase for the rest for the decrypt the rest of the hard drive. And you don't need to necessarily, of course, work with the TPM. You can have a file which contain a text, and you can use the text basically to unlock the encrypted partition. And I have a fallback here if something goes wrong, and then it actually prompts. If you don't do that, it will not prompt you. So I am basically enforcing the system to prompt me if something goes wrong. And here you can see the key file. Previous slides, you may have seen that we have the key file at CD keys, which actually unlocks the partition. And instead of, for example, using that key, you can actually keep the key file here. And then this makes like some sort of, little bit more enhanced security. You must have the USB drive plugged on that machine. If it is not, system will not boot up, or system may be boot up, but you will not be able to access the operation system, and user space won't be available. And after that, everything you do here is actually takes place after the operation system boots up. So because you are basically creating script file and placing there, and after that you need to update the init RAM again. So everything goes well when you boot up the system. You will not see an error message, but I still recommend you to not to do this at once. What you can do, you can basically kind of have fun with it. Just have one USB drive, know the UAID, and then basically put there a couple messages. What will happen when the machine boots up? After the early boot, you will start seeing your custom messages, and you will know that, okay, everything works. Because some reason maybe the script in the local tab will not work, and you will need to know that. Otherwise, if you are like depending on this right away out of the box, you won't be able to maybe access the operation system. So it was not scary at all, right? Thank you for all. If you have any question, please don't ask.
We have some questions on Slido. So first, did you try any automated solution like, for example, Clevis plus Tank or system decrypt and roll?
Yes, I tried both of them. Maybe because I couldn't figure it out. Clevis seems actually simplify like maybe 30-50% of this process. It takes over some of the responsibility, and you don't need to configure everything. But I couldn't just get and set it up on Debian. But if you can figure that Clevis, yes, that's actually a really nice way to go.
The second question is, was there any restriction to decrypt disk in offline mode? Or what is the reason to not get the decrypting key from the server via secured connection?
You can actually get it, but you need to, it depends where you want to do it. During to like an early boot, if you configure the init RAM, you can access actually remote source. You can actually get the key, for instance. You can unlock the partitions, and you can just get rid of that key. This is about the basically your decision, also capabilities, and the know-how you have. Like what you would like to do. This setup is focusing on on-premise, but also offline mode. So USB drive, that's why is used, and you are not accessing the internet.
I see questions. So.
Hi Emrah, I'm Otakar, and my question is: you first went through like decrypting the disk and encrypting the disk and encrypting the boot partition, and then you went to automate the process, so you don't have to put in the password every time. And my question is: when you automate the process, then I suppose the decryption keys are stored in plain text somewhere on the device, and if someone stole the computer, he can see the keys and decrypt the drive, decrypt the boot, and basically my
What's-
whole
yeah.
journey would be worthless.
Yeah, I understand. What's the purpose keeping there? So they actually cannot, because if you encrypt the, let's say you have the boot partition and the rest of the hard drive. So you encrypt the rest of the hard drive with LUX2 and the boot partition with the LUX1. So you are keeping the key, right, in the, let's say, etcd key folders. And if you have the hard drive and if you plug in another machine, you will have two partitions. One is encrypted with LUX1, second one encrypted with LUX2. And if you have some like a, I don't know, very fast machine, unless you have it, you won't be able to actually decrypt it because it's already both parties are encrypted. This is actually a really good point because this is how you hack system. Momentarily, things are actually unlocked. In fact, if you are booting the machine, if you encrypt the boot partition, you will be prompted 2 times. First during the early boot, and after that 1 more time. So basically during the early boot, it will ask you to enter the passphrase, and after the boot process is almost done, it will ask you 1 more time to encrypt the boot partition again. So during that time, if you have somehow access to this process, then you may get the key. But if you only have the hard drive, it should be secure because both partitions are already encrypted. Make sense? Okay.
More questions?
One addition, the unlock key is present in the TPM, and the TPM will only give it out if the system state matches. So if you use secure boot with your keys and only your keys and seal the secret to that state of the machine, it will not release the key to anyone because the system will not allow anyone to boot the system from like a flash drive with Ubuntu. And if you turn off secure boot, the system will not be in the state that it would be expecting the secure boot and like unseal the key, and it will again not like give the key out. There was one moment, one slide where the UEFI binary for group was presented with like, let's add the secret to the UEFI binary. Please not do that, because that would be the place where you could steal the key. If you avoid this place, then it should be secure.
And maybe it's how it works in Windows, because if you use the disk encryption, you don't need to give any password. It's encrypted. If someone steals your computer and left the secure boot enabled, he could try to trick the OS when it boots to get to the data.
You wanna come
We
here?
have a discussion, so
I am standing. I will rather.
No, there are 16 registries, like PCR registers, and you can seal the system state to as many of them as you want. There was like 4 of them on the slide. The 5th is the 7th register, which contains the secure boot state, and you can use more. You can use other ones that contain the partition table layout, the boot loader binary hash, and more. So Windows uses those additional registries with the additional like states, and they pre-compute the state before you reboot. So the key is only released from the TPM for Windows if the other registries match as well.
don't argue with him. He worked with me in Avast, so he should know. So any other question? If no, so there was one last mention. It was not question, but it's on the slide. Pavel, you remove it, so can you please bring it back? No. Just a minute. Yeah, I like it, so I just wanted to read it. This was a note. I just don't understand why Michal is so afraid of it when it's so straightforward. Yeah, no. Is it for Taos? Yeah. I don't know. I think that's all. So one more time, thank you, Emrah. Or you can, take it offline. So, but okay.
like I understood you are from Prussia as well, or not?
No.
No, I see. Because like for this all was for on-prem, and Prussia is running on public cloud providers, right? So this not so applicable for you guys, or are you using secure boot somewhere?
I can share it in offline mode.